So I think I've started the recording. Okay. Yes. So I think I will we'll just start now. Okay. So again, so we are doing online. So in case you have any question, right? So feel free to say type your question in the chat box or chat rooms, or you can just sometimes unmute yourself. Okay. So you can just say ask your question. Okay. Or you can just save the question, say during the break or after the class. Okay. So in case you have any questions, so feel free to stop me anytime. Okay, so if you have no technical issue right now, so let's start it, okay? So last time we stopped at talking about the mobility, right? So we stopped at mobility. So kind of the idea for mobility means that if you apply a force, right, to a particle, if you know the mobility, right, the parameter like B or the Z, right, the electrical mobility or mechanical mobility. So you can have a quick idea, right, about, so what's the eventually, right, the velocity, or sometimes we call it drift velocity, right, if you apply external force, okay. And then last time we stopped is in the electrical So we stop at this, we call the electrical mobility. So there's some reason why we want to learn this mobility, because I just write down the equation in case you forgot. So Z is the electrical mobility. So by definition, right? So it's the kind of the velocity, right? And then divided by the E. So the capital E here is the electrical field strength, right? If you remember. The E here is the electrical field strength, okay? And then this is time V is the velocity, right? Eventually you achieve, right? Or we call the drift velocity here, okay? And you can calculate this. Okay, so N times is basically the number of the charge so you have on the surface of the particle, right? CC here, so if you remember, this is called the Cunningham correction factor, right? Correct the slip factor, right? And then this is zeta, the viscosity of your fluid, and also dp is the size of your particle, right? dp is the diameter of your particle. So of course you can see, right? At a given force, if your size increase, right? So your z will decrease. Of course, the mobility, right, will decrease because you become more mass, right? So it's more difficult, right, to move if I'm given a certain force. Here, I just want to give you some ideas of why we are interested in this electrical mobility. One of the reasons is if you want to study the aerosol size, say some ultra-fine particle. So if you want to size or measure the size of some ultra-fine particle or some submicron or nano-sized particle, right? Because the particle is very small, so one implication is that it's very difficult to measure so the size using the optical method. For example, due to the light scattering. So it's difficult to measure optically. So due to weak light scattering. Right? So I think this is a kind of intuitively thinking, right? So let me get a pen, sorry. So you can imagine, right, if your particle size is very small, right? So if you have some idea how we measure the aerosol size is, so you can have a particle coming in, then you apply a laser, right? And then you can measure the scatter light, okay? And then somehow this is another way to quantify or measure the size. But you can imagine, right? So if your particle size getting smaller and smaller, right? The intensity of this scatter light, right? Or reflected light will become very weak, and then you cannot give a nice signal. So this is why it's very difficult to measure, right? Small particle using this light scattering or optical. So how to solve this problem or to size a small particle? So what we try to do is that we try to charge the particle. So in the other way, to measure this small particle. So first, your aerosol or your particle, say, can be charged. Okay. So you can charge, say, by attach some gas ion. Say attachment of some gas ions on the surface. Okay. And then you get some charge. And then if you have a charge of your particle, okay, somehow what we can do is we can play around with this configuration. So I think you learned this, see this device, similar device before. So for example, we can apply an electrical field across these two plates. For example, you can have a negative charge and then have positive charge. Right, so then you have across the field strength, okay? And then what happens is that you can also introduce your aerosol or your particle, right, into this between these two plates. So you can introduce some aerosol at a given size, a given speed, velocity. Okay. So let's say this is your x-axis. And then if it depends on the charge of particle, so your particle can carry some charge, and then you have a velocity here, right? And then you can apply an electrical field, right, or electrostatic force onto this particle. So eventually you can see, I can project the trajectory, right? Depends on the charge of your particle. But let's say, right, so you can have a particle like this, right? The trajectory, say, depends on the size or the velocity, right? So you can have different trajectory, right? Appreciate this are two plates. Okay, so this is depends on velocity, your charge of the particle, and also the field strength. So different particle size, right? Even at a different condition, right? So you can have different trajectory, right? So therefore, you can see that so we can use this technique, okay, or this approach to size a different particle, okay, to size a small particle here, okay. So one thing to do this is to just we have been discussed, or we give a name for this device. Okay, there's a name. So for those you are interested to measure the size distribution or the size or the mass of small particle, so you will always come across with a term called the DMA. DMA means the differential mobility analyzer. So this is a very important device for ambient aerosol measurement. Okay, so you will always come across with this device. We call the DMA, differential mobility analyzer. Okay. So what we don't go into detail, but typically the configuration, you just you make this the two plates, you put it vertically. So you have a column. So we kind of have a column like this. Okay. And then you can introduce your particle, okay, on the top. So remember, this is symmetrical column, okay? And then you can introduce your aerosol on the top of the column. Of course, this particle will be charged, okay? It's charged already, okay? So it's some charged aerosol. And then you can introduce to the aerosol into this with certain speed. And also you can apply a voltage, right? You can apply an electrical field, right, across this column, right? And then what will happen, the idea is, right? So then the particle, right, at a given size, so that means that you can see you have some charge particle. So they can travel, right, with the velocity, right? So how you can determine this velocity here? Okay, so basically it's a balance, right? So you can imagine if velocity is just a force balance, right? Say balance are two forces, right? So of course, one is the called the electrostatic force, right? So you can apply an electrostatic force to this particle, right? So we can apply an electrostatic force. And also, of course, when you have a movement, right? So you have this that we call the drag force, right? So you can also have the drag force, okay? We call the aerodynamic drag, right? So you balance this force, okay? So basically, these terms, what we're talking about, the velocity, right? So it's more like what we talk about the electrical mobility, right, of a particle here. We are talking about here. And then you can see that, so when you have a particle here, right, if you have different mobility, so you can imagine, so if I introduce the particle at the same position here, but depends on their electrical mobility, right, of particle. This, of course, you can see this also depends on the size, right? So it depends on the mobility. So can you imagine, right? Of course, the mobility means depends on size, so they can have different trajectory, right? Or I can argue, right, under a certain condition, right? So I can draw different trajectory here. And then if you say this is the column, so this is where you introduce your aerosol, right? And then depends on the trajectory, right? So you can see some particle, right? So we just hit the column here. But at the right condition or right size. So let's say I put an exit here, okay, for your column. So at a given size, certain size, right, of your particle, okay. So in that case, your particle can leave the column, right? Do you see the point? So I can introduce the particle, right? This charged particle with different size. Of course, then they will have different mobility, right? In the column, so they have different trajectory. So therefore, under certain condition, only a certain size of your particle, right, can exit the column, right? Do you see my point? Because you can see too big or too small, so you cannot exit the column, right? Somehow you just impact, right, to the electron here. So this is more the electron. We apply voltage, right? So therefore, you can see here is you can imagine, right? So let's say I introduce a particle with different size here. So let's say this is size at the top. But you can imagine, right? After passing through this column, when I measure the exit, right? So you only have a very narrow particle, right? Only particle with certain size, right? Mobility, right? Can leave the column. So therefore, you can see this is how, or you can say size or select the particle size that you want, okay, based on the mobility. So because too big or too small, you cannot leave the column. So therefore, this DMA is a very important device that people use to do the size measurement of the aerosol. Okay, then you can ask also how you can measure a distribution, right? So we're interested to look at different size, right? How you can do the size selection. So you can see here, right? Is one thing is you can play around with the voltage. If you remember your velocity, right? Your electrical velocity. So that will depend on your size and also depends on the voltage you can apply, right? The electrical field strength here. So I can change my voltage. So I can change the voltage, right? Apply to this electrode, that means I can change the electrical field strength, right? Then I can just select the size, right, at the right speed, right, of the right size that to pass through this column, okay? So therefore, to do different size measurement, Okay, so let's say I want to do different size measurement. So what I can do is I just scan through different voltage, right? So if I apply different voltage, then you have different electrical field strength, then your velocity will change, right? And then in that case, I can size the particle that I want. Okay, so this is how you can eventually by changing different voltage, then you can have different size. Okay, so give you different size here. So this is how we call the electrical mobility analyzer DMA. So remember, so I hope that you get some ideas about this term called DMA. So because this is a device that we use, okay, to measure the size of some small particle, okay, and then usually it's less than 1 micron, okay. So for particle less than 1 micron, maybe around 10 nanometer to 1 micron, so you can measure by this DMA. We call the differential mobility analyzer. So that's why somehow I hope that you will have some idea about this electrical mobility, because later you will see that when you talk about the size of the particle, you can have different definition. Here, the size you measure by the DMA is called the electrical diameter. Okay, electrical mobility diameter. So we're going to come back to this, but I just want you to give you some ideas about this DMA. Okay, so this is a very important device for aerosol size measurement. Okay. So are you okay so far, like this, the writing on the board, and also you can hear my voice, right? So since the first time we do the online, you are okay, right? So it's clear, right? So any question? So you're okay, right? So again, if you have any question, yeah. So any questions, just feel free to let me know. I'll type in the chat box. Okay. Okay. Good. So now we are going to move on to talk about the size of the particle, or sometimes we call the shape of the particle. So I think I also get the question from the student is so how, when we do the derived, I talk about the Cunningham, the Stokes equation, right? I think some student asked me how to do the correction, right, for non-sphere particle, non-spherical particle. So of course, most of the time when we talk about the aerosol size, right, or when we derive the equation, right, the drag force, so we assume we have a spherical particle, right? So all the discussion, right, is so far, right? So we rely on some spherical particle. But of course, we know that many ambient particle, right, or some engineering generated particle, or nanomaterials, or bioaerosols, so they are not spherical, right? So I think you all know, right? So we're non-spherical. Okay. So then somehow we need to account for this the shape, right? So therefore we need to somehow to look at, we call the shape effect. Okay. Onto the particle motion. Of course, we are talking about the particle motion, right? So we want to look at how the shape effect can affect the particle motion. Okay. Here. And therefore, people will introduce a factor called the shape factor. Shape factor, kind of X. Because you know, so when we talk about the motion, right? So we are interested in called the drag force, right? The aerodynamic drag on the particle, right? So therefore, this shape factor, by definition, you can argue, right? Is we call, so let's say the actual drag. So if we know the actual drag on the particle, and then over, so you need to reference, right, to something, right? So when we derive the equation or when we use a discussion, right? So therefore, this shake factor is the ratio of the actual drag on the particle to the drag, okay, on the sphere, okay, of the same. So let's say you have the same volume and density. So you try to, this is called the shake factor. So let me take this out. So this shake factor, so we are looking at, so in case you know the actual drag on your particle, then you compare to some reference, right, particle. So you're looking at a drag on the sphere, of course, we always a sphere, and then have the same volume and the density of your particle here. Okay. So so what's that mean? So now that means, for imagine, right? So this is your actual particle. So you have an irregular shape, right? This is your irregular shape. So what will happen is, so we try to first find a particle, okay? So kind of find a particle. This is a sphere, right? So you find this particle, okay? This is your real particle, have irregular shape. And then you try to find a particle, sphere particle, okay? And then have the same volume and the density of this actual particle. Or you can argue, maybe another way to think about this. So let's say you have a gold, okay, you have some gold particle. And then you can somehow melt this gold, right? So as is, so you can melt the particle, right? So the particle, and then you melt. And then to form a spherical particle. Right, so you can imagine, right? So the idea is that if you have a gold particle, right? Okay, so you have a irregular shape, gold particle. And then you can melt this gold particle, right? You can melt this gold particle, and then you melt it, and then you get the sphere particle, right? So then in this case, so if you just melt, you can imagine, right? So you have the same volume and also the same density, right? You will have the same volume and same density of your actual particle, right? Are you okay with this? So basically, just imagine you just melt a gold particle here. So therefore, if you form this, you have to agree with this, and then you form a stable particle, then you can look at the diameter, right? We call this a dVe here. This is called the volume equivalent diameter. The volume, okay, equivalent diameter, dVe. You try to find a particle, right, at the same volume and density as the particle you have. Okay. This is that's why now you form this spherical particle, right? And then you have this we call the diameter, right? The volume equivalent diameter. Are you okay with this? Okay. So now, if we're going to apply to these equation, right? Okay. So now, if you can determine, right? say the drag on this volume equipment, or this is like a spherical particle, right? If you can calculate the drag force on this spherical particle, and then you time this x, right, the shake factor, then you can get the actual drag, right, on this one. Do you see how you do this? So in case you can try to find this kind of this particle has the same volume and density. So this one, okay, you can calculate the drag force, right? So this one using the equation or discussion we discussed before, right? And then you times this we call the shake factor. In this case, then you can get so-called the actual drag, right? So therefore, if you agree with my argument, so if you say this is the actual drag, you try to find this drag force onto this particle, right? So this will be equal to so basically this component, right, tells you the drag onto this kind of a hypothetical spherical particle, right? You know this, you try to find a spherical particle with the same volume density. You calculate the drag on this one, okay? But you know this is not equal to this one, right? Not to the drag on this actual particle. Then you times this shake factor. So then in that case, this will give you called the drag force. We call it the actual drag here. Right, so this is called the actual drag. So this is the one way people to looking at this. Okay. So then you can now if you know this is called the shake factor, then you can correct this, right? Shake effect, right? So by looking at this, you're looking at this called the shake factor. So most of the time, so you have a different, you have a larger drag. So most of the time, so the drag will be larger than 1. For example, most of the time, if you have a cube, okay, so that means that if your actual particles have a cubic in shape, okay. So therefore, the shake factor for cube is 0.108. So this is more like when you look at sodium chloride or marine aerosol. If you have dry marine aerosol or sodium chloride, remember you are measuring more like a cube, right? Cubic particle. So you need to correct this drag using this shake factor. Or sometimes you can have a 2 particle. So the shake factor people determine is about 1/2. Sorry, 1.12 here. So you can have different shape. We don't go into detail, but the idea is so you can do this shake correction. Okay, so you can find this value for different shape, and then you can just do this correction on the drag. So therefore, you can see that when you talk about the size, okay, of this particle, so it's hard to give you a physical diameter, right? And now you can have this we call the volume equivalent diameter. But of course, if you apply this called the volume equivalent diameter, if you look at the motion of a particle, okay, then you need to remember you need to correct the shape. Sorry, this should be O. And you call this a shake factor here. So any questions so far? Okay, that's a good point. So how we can get this shake factor, right? How people get this shake factor? So one way to do this, right? So you see here, right? So basically, you can, for example, give you one example for this sodium chloride. Okay, sodium chloride. This is more a cube shape, right? So you can use like some cubic particle, like sodium chloride. You generate this particle. Okay, so then you can measure like some velocity, right? Drag velocity or drag on this one. Okay, on this some sodium chloride particle, and then you try to also this can be calculated, right, by the equation. Okay, so this is come from the measurement. Then you can just compare these two. Then you can take the shake factor. So the actual drag has to come from the measurement. But the drag on the sphere of this one, right? This is the volume, right? The current diameter, right? This is hypothetical, right? Spherical particle. You can calculate using the equation, and then you can determine the X factor, the shape factor. Do I answer your question? Because the actual drag you need to do the measurement, right? So this one you need to do. This comes from the measurement. Good. Okay. So any other question? Okay, then we'll move on. So again, so you can just save your question, say during the break or after class, or you can just send me an email later. Okay, you're welcome to talk to me. So now you can see another idea is to describe a irregular shaped particle. You can kind of using this we call the volume equivalent diameter, right? So you assume this particle can be represented by this volume equivalent diameter. Because the thing is to describe the shape or to describe the size of this irregular particle is difficult, right? So you cannot assign a diameter, right, to this irregular shape. Okay. So there's another diameter. So we should have some idea. It's called the aerodynamic diameter. Okay. So what's that mean? So when we talk about this aerodynamic diameter, so let's say we call this a dA. dA. A means the aerodynamic diameter. So let me give you the definition first. So this is called the diameter of a sphere or spherical particle. So let's say spherical particle. So having a unit density, remember, so this is some definition, having the density, we call unit density means the density of the particle you're looking at is 1 gram per cm cube. So this is density that have the same, remember now this is term, the same settling velocity settling velocity as the particle that you are interested or in question. So what's that mean? So that means in case you have these irregular particle, okay, so then in case you know the settling velocity, okay, that means the terminal velocity, right? So we talk about the terminal velocity, right? But the settling velocity means the terminal velocity. So in case you know this real particle, okay, so you know this terminal velocity. Try to make up some number, say 1 millimeter per second. Okay, so you know this is the settling velocity or terminal velocity of your real particle. So what you try to do is you try to find a particle, also a spherical particle, have the same settling velocity, means you also have 1 millimeter per second in this case. So you have a spherical particle, okay? But the thing is, the density, okay, the density for this particle, I assume, is equal to 1 gram per cm cube. For example, your real particle, right? So of course, a different shape, but that's the density will not be equal to 1, right? So let's say your density can be some number, say 4 gram per cm cube. But we don't worry about the density of your particle. So I try to find a particle spherical in shape, okay, and then have a diameter called the dA. I have the same settling velocity, okay. Does it make sense? Are you okay with this? So this is by the definition, okay. So now we are looking at this spherical particle. So what the difference is, for the volume one, so you also assume you have the same density, right? So the density of these two are the same, right? So if this is the rho, this is the same, right? The density are the same. But here, remember, this will be highlight is the density is the 1 gram per cm cube. And then you're looking at they have the same settling velocity here. So this is the definition of what we call the aerodynamic diameter here. Do you have any questions so far? So then, so you may ask why we want to do this, right? Because settling velocity, okay, it's something that we can more easy to measure, okay. Okay, so but the idea is that if you want to know the density or the shape of some real particle, it's very difficult. But the settling velocity, so we have the instrument. So we're going to show you the details later. So you can measure the settling velocity of a particle. Okay, so you can get this number. But the problem is you don't know, right, the shape or the density of your particle, right? So therefore, hypothetically, so we try to think about, you present these value, right? This is what you measure. You present these, okay, as a aerodynamic diameter means you try to find a particle, okay, spherical in shape, have one density, right? Unit density, then have the same settling velocity. So you measure this one, but you don't know this, right? You don't know the shape or the volume or the diameter. You try to use this number, and then you try to find a particle with this we call the aerodynamic diameter. Okay. So that's what what the people present to you is the aerodynamic diameters. Okay. So do you have any questions so far? Okay. So now, so you can see we introduce different diameter, right? So you can see this is your actual particle, but most of the time you cannot say give a physical parameter, right? To say the diameter of this particle. So you can different way to present, right, or describe your particle, right? Your aerosol diameter. So let me give you a quick summary. So you can have types of, so I know that there may be some confusion to you. Okay, so let me go into some details here. So you can have different types of aerosol diameter. Of course, one thing is if you go to the microscope, you do the scanning and then you have the image. So of course, as usually we have this, we call the physical diameter, right? So let's say if you have the, if you're lucky, right? So we have your actual particle is a spherical particle, right? And then you just look at the geometry, right? Of your particle diameter, right? This is more like if you have this geometric diameter. So you can get this. If you collect some particle onto some filter, you do the look at the microscope, right? Then you can, if you have some spherical particle, right, or your different shape, then you can assign called geometric, called the geometric diameter or physical diameter of a particle. And also, we just introduced this we call the volume equivalent diameter, right? So that means that dVe here, okay, dVe here. So because most of the time, so if you look at the microscope also, right, so you will see your particles irregular in shape, right? So we always have this irregular in shape. So what we try to do now is to try to get you a particle, right? Hypothetical particle, right? So spherical in shape, have the same volume, right, and density of your actual particle. So then you have this DVE here, just like we present here, right? So it's also one type. Okay, you assume you have the same volume and density, right, of the particle. And then we have this aerodynamic diameter, dVA, for dA. So sometimes people will plot the diameter using this aerodynamic diameter. So now you know, right? So what you are looking at is you have a particle, right? And then you have a settling velocity. And then you try to find one have the same settling velocity. I mean, they have the same terminal velocity. But now you find this diameter is also as imaginary particle, right? So this is a dA. But remember, so because I also don't, the thing is, to apply this volume equivalent diameter, somehow you want to know the density, right, of the particle. But if you don't know the density of the particle, right, so I cannot assign like this. So therefore, what I try to do now is I just assume my density is 1 gram per cm cube. Okay, but they will have the same settling velocity. Okay. Are you okay with this? So then later, there's be one more. We call the electrical mobility diameter. So we come back to this. Okay. But the idea is now, I hope that this is a quick summary. So at least you have a one more called the electrical mobility. So we're going to go back to this. But you have this more the physical diameter. I think you have all the ideas. And also you have this volume equivalent diameter, right? And also you can see, you can have this we call the aerodynamic diameter. So by different definition here. But one more thing is, I want to come back to here. So now you know the definition of your aerodynamic diameter, right? So of course, so we want to also calculate the terminal velocity, right? Maybe let me see. Okay, let's put it this way. So if you remember, right? So for your aerodynamic diameter, right? So you try to calculate the based on the settling velocity, right? Here, okay. So therefore, in this one, in this case, right, this aerodynamic diameter, you can also calculate the terminal velocity, like say VTS, or we call the settling velocity. Here, right? So you know this should be the same. So given this size is dA, the density, so you can also calculate, right? So we show you this how you calculate this. Okay, so this equation tells you, say, if you have this aerodynamic diameter, right, dA, and then this density is 1 gram per cm cube, and then gravity. So you do this Cunningham correction factor CC. Remember, this is a function of your particle size, right? So that's why I put a dA here, right? And then divided by 18 pi, this is zeta, right? Zeta here means that the viscosity of your fluid. Then you can calculate the terminal velocity, right, for this particle. And then this, the settling velocity will be equal to this one also, right? So I think because of this equation, right? So we showed this before. Okay, sorry, I guess some comment from the chat room. So let me see. So there's a comment. Sorry, sometimes I missed the chat room. So let me repeat the question here. So can I put in this way? That size is represented in some way by velocity. As the velocity is easy to measure. Yes, good. Yeah. The other way is you look at this terminal velocity or velocity. Okay, so good point. Is something we can more easy to measure, right, or determine, right? So you're right. So you can also say that because velocity is something more easy to measure. Because you can see here, right? This is a certain velocity or some velocity, right? So we can measure it, right? So it's more easy to measure. But if you want to say measure the shape and also their density is very challenging, right? So for a very small particle, you can imagine, right? It's very difficult to know their shape and also their density. So therefore, velocity is a more like a parameter, right? So that is more easy to measure. So you're right. To answer your question. So this is question. Okay, if we want to present FD, the drag force with dA, right? So what equation will be? Good. So if you remember, right, for the drag force, so let me see. So I think we have the equation for the drag, right? So if you remember. So now we are looking at just remember this equation is for the settling velocity, right? So now there's a question from the student is that we just want to look at the drag, right? So do you remember how the drag, so we can determine how the drag, okay? So if you look at the drag on this particle, just this particle, right? So FD, so what would be the drag of this aerodynamic diameter? So you still use the equation, right? 3 pi rho v now. So what's the diameter here? So you are noticing the dA, right? So this will just give you the drag on this particle. No shape correction, okay? Just for this spherical particle. So this is the equation we showed you before, right? So this is the drag. Is that okay? I answer your question. So if you just want to calculate the drag on this particle, so we're going to use this equation. But you don't need to worry about the shape factor, right? Because your question is you just want to calculate the drag on this one, right? To answer your question. Okay, good. Thank you. So then let's say we can continue, right? Good. So I can also calculate, right? So let's say in case I want to have a volume equivalent diameter, okay? So let me, you can also argue, right? So I can have a volume equivalent diameter. I have the same settling velocity. So I can also calculate, right? So let's say you have this same settling velocity, right? For this volume equivalent diameter. So this equation, is to calculate the settling velocity, okay, with using the volume equivalent diameter, okay. So now there's some difference between these two, right? Okay. So for the volume equivalent diameter, right? So if you want to use the volume equivalent diameter, that means so you try to melt this particle, okay, and then you give this a volume equivalent diameter, right? And then now you have the same settling velocity, right? Here. So you can calculate the settling velocity, right? But now the density, now I will use the dP, right? So you need to know the density, right? dP means the density of the particle. Assume you know the density of the particle. Now you use the volume equivalent diameter square, do the correction. So now the size will be your volume equivalent diameter, right? And then this is 18 times this is zeta, right? Then you times this is shake factor. Because you know the volume diameter, right? Here. So you assume there's a shake factor here. Okay. So to correct the shake factor. So then if you have the same settling velocity, right? So these two values will be equal, right? So they will be equal. Okay, if they have the same settling velocity. So that means that in this case, I can have, so let's say this is your real particle, right? So you have this settling velocity, 1 millimeter per second. So what I can do is I can find a spherical particle, right? Have the same volume and density of this particle, right? Also have this settling velocity, 1 millimeter, right, per second here. And at the same time, I can try to find a particle, okay, spherical in shape, okay, and then just have the same settling velocity here. So I can calculate using this equation. And then if they are have the same value, right? So these two values will be the same. Okay. So then I want to say a few more things. Is so people want to do the conversion here, because you can see, right, from time to time, so we have different types of aerosol diameter. So there will be some relationship between these two values, right? This is dA versus this volume equivalent diameter, right? So there may be some relationship between these two parameters, right? So or you can do some interconversion. So therefore, we want to also spend some time to look at the relationship. Say in this case, between the dVe, the volume equivalent diameter, and also the aerodynamic diameter. So we are looking at, so what are the relationship between these two values, these two diameters, right? There are two different types of diameter, right? So let's say we can, like as mentioned by the student, right? So we are interested in velocity. So let's say if these two particles, the red one, red dotted one, and this one have the same settling velocity. Okay. So this is something that we can measure, right? So I can try to find the same settling velocity. So then I can calculate the settling velocity, right, of these two particles, right? So we'll be using these two, right? So then if I compare these two, so these two should be equal, right? So these two will be equal. So let me write down here for you. So because we assume the settling velocity, right? They have the same VTS, right? So therefore, these two values should be the same, right? So then I can compare. And then now you can see some terms I can cancel out, right? So this term, so you don't need to bother by this term, right? So some terms can cancel. And then if I write down this, so you can see there's a relationship between these two parameters. This is the aerodynamic diameter, right? Square will be equal to So if you know the density of the particle divided by the unit density, so this is the unit density, right? It comes from here. And that will be equal to 1 over the shake factor. This is also the one we are interested, right? PV, the volume equivalent diameter, right? This one, okay. And then you just correct the slip factor, right? Because remember, this is the size dependent, so you need to use the relevant size, right? So they give a different value. Okay, so this equation kind of tells you how to convert, right, between these two parameters. Okay, so this is something here. And then we can just do some simplification. Okay. So if you remember, right, when we talk about this slipping correction factor, right, or non-slip correction factor here, Cunningham here. So you need to define the regime, right? So whether you are in a continuum regime, right? So that means if you still remember, right, your Nusselt number, right, is the lambda divided dp, right? For the continuum regime, right? So you know that when we derive the drag force, okay, so continuum regime, so the CC can be neglected, right? So it's negligible, right? So it's close to 1 because we derive this, right? So you don't need to do the correction, right? Negligible. So therefore, this term is close to 1, right? Because you know when we go to the free molecular regime, then this number becomes bigger and bigger, right? When your size decreases. But we are in a continuum regime, right? So this factor will be close to 1. So therefore, you don't need to worry about this correction, right? So therefore, the relationship between these two parameters these two diameters, okay, in the continuum regime will be this aerodynamic diameter. This is the volume equivalent diameter. So the relationship is you need to know the shake factor and also the square root of the particle density. This is 1, and this is the shake factor here. Okay, in the continuum regime. And then if you go to smaller particle, so then you cannot ignore, right? This is a correction factor, right? If you remember, for small particle, we cannot ignore the correction factor, right? The CC, the Cunningham correction, right? And then this value is getting bigger and bigger, right? When size is smaller. So therefore, if you remember, if you consider a free molecular regime, or we call the non-continuum regime, that means your particle size is very small. So your Cunningham correction can be approximately, say, the size of the particle 1 over your size particle. So we know that when your particle size getting smaller and smaller, right, the correction factor will increase, right? So therefore, when this size decrease, the correction factor will increase, right, to correct the non-slip factor, right? So therefore, you can also put this back to these two here, right? So therefore, if you're doing this, then you will have this called the dA. Square. So I'll just give you the result. So now in this free molecular regime, the relationship between these two parameters, this is the aerodynamic diameters equal to just the rho p, okay. This is the density of the particle, remember, so this is the unit density, 1 gram per cm cube. Divided by the 1 over the shake factor, this is your volume equivalent diameter, okay, under the free molecular regime. Okay. So then you may ask, so why you want to do this, right? Is because, especially this free molecular regime. So there's some practical reason to show you here is because sometimes if you look at this free molecular regime, of course you're talking about some small particle, and also this is important for this free molecular regime. So when it will happen is if you want to do the measurement, just to highlight, important for, say, the aerosol, some aerosol mass spectrometer, and also we call the low pressure impactor. So you may ask why, right? Because remember, for this free molecular regime, right? So the idea is you're looking at the reduction number, right? Say dp. dp is also the character time. So you are looking at now the fleeting part, right? This is your gas molecule. So this is your particle, right? So it behaves like this. So right. So your lambda can also increase, right? Depends on the pressure. The reason is at low pressure. So you know, you can imagine, right? At low pressure, what will happen to your lambda? The mean free path of your gas molecule at low pressure, it will increase, right? So you increase. So this is, so therefore you will go to in the low pressure. So most of the time, so we will in this we call the free molecular regime. Okay, we are not in this contained regime because in the low pressure, okay, your lambda will increase. You have a larger Newton number. Okay, so in this case, so you will have this in this called the free molecular regime. And also most of the aerosol mass spectrometer, so we operate at low pressure or vacuum, sometimes close to vacuum. Okay, or vacuum. So if a vacuum, right? So you can imagine if a vacuum, you only have a few gas molecule, right? So your lambda will become very big, right? Remember the lambda, I mean the mean free path of your gas molecule, right? So very big. So very likely this instrument, so when you operate this aerosol mass spectrometer under the vacuum condition or low pressure condition, so we will have this we call the free molecular regime. So we are in this free molecular regime. So therefore, the particle size you measure here. Okay, so you need to do this correction. And also there's a name called the vacuum. They gave a specific name under this regime. It's called the vacuum aerodynamic diameter. Because you are measured under this vacuum or low pressure condition. And then you need to use this free molecular regime correction equation here. So therefore, this equation, okay, and also the free molecular regime. So now you have some more idea is so why we care about this free molecular regime is when we do the measurement, okay, in some device like the aerosol mass spectrometer or some impactor, low pressure impactor, we are operate at low pressure. So what's the meaning of low pressure or vacuum means your lambda become very large, and then you are looking at a large Newton number. So therefore, you're going to the free molecular regime. Okay, so you are not in this continuum regime anymore. And then therefore, they give a name. It's a command called the vacuum aerodynamic diameter. Now you have the idea why they put that name vacuum, because you measure this diameter under the vacuum or low pressure condition. Okay, so I just want to give you some more ideas here. Do you have any questions so far? Okay, if not, because of the time, so let's take a 10 minutes break here. Okay, then we'll come back at 12:45. Okay, so we take a 10 minutes break here. So in case you have any questions, so you're welcome to ask. Okay, so let's take a break here. Before we continue, do you have any questions? So you want to ask? Just one more comment is you can see, right? I think we have spent quite a lot of time, and also we emphasized many times that this aerodynamic diameter, right? So it's usually the one we measure, right, from the device, because basically we just measure the velocity. Okay, we don't need to worry about like the density or the shape, right? But you can see here that the problem is you can see most of the time you will not use this we call the volume equivalent diameter. Okay, in case you do the measurement, you get the aerodynamic diameter, right? Velocity. The problem is if you want to know this we call the volume equivalent diameter. So you need to know the particle density and also the shape of your particle, right? You need to use the shape. So it's very difficult to obtain, right? So the ambient particle is you have many different shapes and also densities are known. So therefore, usually people will not use this we call the volume equivalent diameter. So most of the time you will see this aerodynamic diameter. And also I want to highlight is, so why I also want to spend some time in this vacuum or free molecular regime or vacuum aerodynamic diameter. So this is the term vacuum means how you measure your aerodynamic diameter, right, or your velocity. Because the problem is most of the time when you do the measurement, for example, you have some idea. So for like the electrical field or some mass spectrometer, right? So you need to under the vacuum condition, right? So you need the vacuum condition. So therefore, when you look at the aerodynamic, you can argue, right? So you can measure under ambient condition, or you can also measure under low pressure or vacuum condition. So what's the indication is most of the time, like the DMA I just discussed. So you are looking at the vacuum condition, right, in the DMA, right? So yeah, has a mutual field. So therefore, we are looking at some vacuum condition. So therefore, we are always looking at this free molecular regime. Okay, so I just want to pay attention because I even have the same particle size. So it depends on the pressure, right? So you can fix this one, but depends on your condition, right? Your lambda will change. For example, in the vacuum, so the lambda will be very big, right? So then you go to this free molecular regime. So then you can argue the aerodynamic diameters or the parameter you measure. So you're under the vacuum or free molecular regime. But you have the same particle size, but you're under ambient condition, right? Then you are looking at maybe some continuum regime. So this is why they introduced this vacuum diameter. Just to give you a more information is, so you also have to pay attention. So under what condition? So we measure this velocity here. Okay, then one more thing we want to talk about the relationship is the DMA, right? So we just spend some time on the differential mobility analyzer. Okay. So then in that case, the diameter we measure is called the electrical mobility diameter. So there's another types of particle diameter. So now this is become, we call the electrical mobility diameter, say called dm. So how you get this is we use the DMA, right? So we show you the DMA. What's the meaning of this called the electrical mobility diameter? So this tells you the diameter, okay, of a sphere. So with the same migration, velocity, or you can just argue it's by the velocity, okay, in a constant electrical field. So that means you don't change the electrical field as the particle in question. So it basically means that you are looking at the mobility, right, of your particle in the electrical field. You try to find a particle, right, spherical in shape, and also with a diameter dm, and then have the same mobility. Okay. So basically, the argument is you have the same mobility here. The thing here is that means you have the same electrical mobility, right? That means the C here. So therefore, if you agree with this, then I can have this dm, right? So dm. So let's say if you look at this, we call the electrical mobility, right? So we talk at the end, at the start of today's lecture, right? C. So if you remember Z equal to NE, right? You do the Cunningham correction. So this is the electrical mobility, right? This is the number of the charge of the particle. This is the Cunningham correction using the diameter, right, of your particle at dm. Okay. And then you're looking at this 3 pi zeta and then also the dm here. This is the electrical mobility. And also you can compare with a volume equivalent diameter. So basically here means you have an irregular shape, okay. You have the same electrical mobility, right? The same electrical mobility. And then you can also, for this irregular shape, like I mentioned, right? So you can also try to find a, right? This is a V, DVE, right? Same volume, same density, and then with a shake factor correction, right? But they will have the same mobility, right? Same. So therefore, these two are equal. Okay. So if these are equal, so what we try to play around here. Okay. Good. So there's another question from the, before we continue, so there's a question from the chat room. So why many instruments operate in the vacuum condition, right? So is there any advantages? Okay. So let's say for the DMA, okay. So you know if you want to charge the particle, okay, or avoid the loss of some of the electron, okay. So therefore somehow you need to operate under the vacuum condition, right? And also if you know if you want to have some ion, for example, the mass spectrometer, this will involve some ion, right? Detection of some ions. So to avoid the loss of the ions and also consider the motion of the ions, right? So you also want to look at under the vacuum condition, okay? And also why eventually you have this we call the low pressure or vacuum is so later when we talk about the cascade impactor. So one way we can enhance, okay, or increase the velocity of your fluid and then to induce some impaction or particle collection. So we create the pressure difference, okay, and then to increase the velocity across some nozzle. So therefore, to have a very high speed, high velocity, so you eventually go to the low pressure regime, okay. So this is, I think this is a more like a practical concern, okay. That's why you want to operate some instrument like under the low pressure and also the vacuum condition. To answer your question. Well, of course, under the vacuum conditions, so there are some disadvantages. Okay, so because maybe you can losing some of your particles or some other species, but more likely is somehow you need to concern with more practical reason. Good. So any other questions? And also, I think if you remember, right? So if you look at the charging, the electrical field, right? So you try to create a high voltage, right? So you're not going to, you don't want to prefer to operate under the high pressure condition, usually under the low pressure condition. So that's another question. Oh, okay. So what's the purpose of introducing like different parameters, right? Different diameter, like the aerodynamic diameter or the dm, okay. So this is a very good point because you can see here, actually you are measuring a different parameter, okay. For example, if you're using some impactor, okay. So what we are doing is we measure transfer, like I mentioned, like you mentioned, like we measure it's more like a velocity, settling velocity, right? So in this case, it's a velocity. So therefore, you can have this dA here, okay. But what about the dm here? So remember when you talk about this, so you are balanced some drag force and also some gravitational force, right? But when you talk about dm, you are talking about some electrostatic force, right? And then balance with the aerodynamic drag force, right? So therefore, when you look at the mobility, or when you look at the motion, right? So you are looking at different conditions, right, of parameters. So therefore, the meaning of the dm, right, this is more like the mobility in some electrical field, right, some charged particle. But you can argue, right, the dm here, right, the aerodynamic diameter is some non-charged particle. So we are looking at different measurement, right, of properties. Let's answer your question. If you look at their physical meaning. So therefore, dm and da, they are not actually the same, right? And also they're given by how we measure this instrument, right? How we measure this parameter. Because like the DMA, they are not measured the DA, right? The differential mobility analyzer, they are not measured the aerodynamic diameter, right? They are measured like the steps, electrostatic force balance with the drag force, right? So therefore, what they are talking about, the mobility is different, or the diameter is different. To answer your question. 答唔答到啲問題？我聽日瞓唔係好渣。Yes, so you can write. So in other words, so like you mentioned, they measure different kind of parameters or minutes. Is that okay? Okay, good. So, but of course, they measure, okay, a kind of a different property, maybe you put out different ways. It's a different property of the particle. Okay, so this is measure the certain velocity. This is more like the electrical mobility. But there are some relationship between, right? So there could be some relationship between. So this is what we are going to talk about, right? So now you have the mobility diameter. You can find another spherical particle, right? At the same volume, same density, the same mobility, right? So using this equation here. So by doing this, so I can also try to find a relationship, right, between these two parameters, right? So these two diameters, right? So I can also try to find a relationship between these two parameters. So then in this case, so you can also have the dm, right? So some parameter like these two I can cancel, right? These ne, 3 pi, zeta, so can cancel. So you can see so you can have a relationship, right, between these two parameters, right? These two physical diameter here. Okay. But like I mentioned, right, what we are more interested is to look at the aerodynamic diameter, right? Aerodynamic diameter. Okay. And then you can see here, right? If you remember, so when we look at this DMA, right? DMA. So what will happen is, so if I try to also link to the DMA, in the DMA we measure under the DMA, right? We try to link to aerodynamic diameter, right? So you can compare. More meaningful is that you want to compare to this we call the vacuum, right? Aerodynamic diameter, right? Or free molecular, right? Because the DMA we also operate, right? Operate under low pressure, right? If you remember. So or under the vacuum, right? Because of the charging, right? Of the electrical field. So therefore, we can also try to relate the dVA dm. So we try to relate these two, right? So what I can do is now you can see this is the volume equivalent diameter, right? Related to the dm. But I also have a relationship between the volume equivalent diameter and the dA, right? Under the same condition, like the vacuum condition, right? So I should use this one, right? Instead of the atmospheric pressure one, right? Oh, that's another question. So how are we going to choose the parameter use? So we go back to this. So let me finish this here. So then the thing is, so you can relate these two, right? So what I can do is I can just substitute this one to here, right? So I can rearrange this equation, try to find an expression for this dVm, and then I substitute this, right? Express this in terms of dA. So then if you do this substitution, so what I'm showing here is now I have a relationship, right, between this mobility, electrical mobility diameter dm with this electrical, so the volume equivalent diameter, right, using this equation. Another vacuum condition, I can also have a relationship between this volume equivalent diameter and also the dA, right, here. So what I'm trying to do is I can substitute this one into here and then get you this equation. So this expression can tell us the relationship between your electrical mobility diameter from your DMA. If you want to convert to be a aerodynamic diameter, dA, okay, under the vacuum condition, okay. Because it's more meaningful to compare under the vacuum, right? So because the DMA is operated under the vacuum or low pressure condition, so you can do the conversion, right? If you from the DMA, you know the electrical mobility diameter. If you want to convert this diameter, okay, back to aerodynamic diameter, okay, so you can use this equation here, okay. So, but now is you can see that will be at least the main message is, so these two are you are measuring different properties, okay, so you are measuring different properties. And also, if you want to do the conversion, in this case, we can see you should have some idea, right, about the shape of your particle, right, and also the density of the particle. If you really want to convert your electrical mobility diameter to your aerodynamic diameter, okay. So that's a two question, right, from the chat room. Okay, so the first question, I will go back here, is how could we choose the different diameters? So I think that will be based on the practical reason, or the things that you are interested when you're talking about. I think more important is you should know that different device, different instrument, give you or measure different diameter. For example, most important is that now you know if you use the DMA to do your sizing, so the diameter, what you're doing, they provide is called the electrical mobility diameter, okay? And then if you say, if you measure some velocity of the particle using some impactor, okay, or cyclone, so you're trying to measure some settling velocity or velocity here. So what the instrument gave you is this we call the aerodynamic diameters, okay? So of course it depends on the interest, okay, in your project or your application. So you'll get different parameter or use different instrument to do the measurement. But what I want to say here is because a different instrument measure different properties, okay, of the particle, okay. So therefore, this is a more important message, okay. So that will be depends on your interest, okay. But more important is to know different instrument, okay, give you different, say, particle size. The information is very different. Does it make sense? So therefore, how you choose this depends on your interest. But you should have the idea is that different instrument. Okay, that means that you should have the idea is DMA when they report the diameter. Okay, so what they mean is called the electrical mobility diameter. It's not the aerodynamic diameter. I think this is the important message. If you want to do the conversion, then you need to do some conversion here. And also there's another question. So why we don't use the electrical mobility diameter with dA to get the relationship? Yeah, of course you can do this. I just write down this here. So you can also have another mobility, right? Using the aerodynamic diameter, you can do the same thing. So it's okay. So I just in case I have the we just have the equation here. Okay, so I just show it here. Of course, you can just directly write down the relationship between the dm and da using the mobility. It's the same here. Because I just given I have the equation here. Does it make sense? And also go back to Dongler's question. That you mean we need to be careful when we talk about diameter? Yes. I think the most important thing is that maybe let me highlight here. I know it's a confusion. So there are many different types of diameter. So then my question is, so why do we need or have so many different types? I think the question is why we have different types of particle, right? Or particle size, or say diameter here. Okay. So if you look at these, all the discussion we show here is actually the instrument. We are not measured directly like the geometric diameter, right? So that means your aerosol sizing instrument. So they are not actually directly measure the size, right? The physical size, right, of the measurement of the particle, right? Are not directly measured the diameter, right? So we are trying to measure the velocity, and then based on that certain velocity, we go back and then calculate the aerodynamic diameter or the mobility. We use the electrical mobility diameter. So instead, is what they try to do, like I mentioned, right? What we are doing, this instrument, maybe put in another way, is they try to measure, right? Another property, right? Of the particle, say the settling velocity, or the electrical mobility, and then convert this property, right? And then you want to convert that to give you the diameter, right? For example, I measure the settling velocity, and then I convert this, give you an aerodynamic diameter. I measure the electrical mobility. I convert this, give you the electrical mobility diameter. You see the point? So basically, the instrument are not directly measure the size of the particle. This makes sense? So that's why when you measure these, okay, I know the settling velocity. Then I kind of give you an aerodynamic diameter, right? Do you see the point? So that's why you see you have different types. The reason is that because the different instruments measure different properties of the aerosol, and eventually you get a size. So therefore you have this, and then different property, right, or different diameter. So you can find some relationship, but of course you can see the relations can be very complicated, challenging. For example, I measure this differential mobility diameter, right, from my DNA. Okay, I'm interested to convert to compare with the aerodynamic diameter, right, under what vacuum condition. Of course, I can do this conversion, but you can see some information, right, like the shape and also the density of your particle is very challenging, okay, to obtain. So this to be just for your information. Does it make sense? So any other question before I move on? I know there's some confusion here, but I think the main message is here. So you can see the aerosol sizing instrument will not directly measure the physical size of your parameter of your particle. You measure like the mobility, you measure the settling velocity, and then you back calculate a diameter. Okay, so this is the main message. I think more important is to look at this section here. So that means you need to be careful when people say, I think the other message just say the DMA, if I measure is a 1 micron, okay, this is not necessarily equal to 1 micron from your aerodynamic diameter, right? So I think if you get this method, I think it's enough. Okay. If you use a impactor, you say it's a 1 micron. That one is the aerodynamic diameter. Okay. And then 1 micron from DMA, this is the electrical mobility diameter. So they are different. Okay, so I think this is more important. So now we're going to move on to the motion, go back to the motion of your particle. Okay. And then one thing is we want to look at, say, called the relaxation time. Say called tau, the relaxation time. Because of, for example, right, if we apply a force to a particle, right, so eventually the particle will adjust to a new condition, right, a new force, right. If you apply a certain force, you have some accelerated motion, right, and then you will eventually go to a new condition. Okay. So these we call the relaxation times. So tell us, okay, tell us the time that a particle, right, needs to adjust to a new condition of force. So basically it tells you so how fast you can adjust, right? So if you apply a force, you achieve a new state here. Okay. So this is called the relaxation time of a particle. Okay. So I just let me just give you the definition of this tau here, the relaxation time. So the tau will be equal to m times b. Okay. So what's the meaning of m? M here means is the particle mass or the aerosol mass. B, so you know this is called the mobility, right? Mechanical mobility. Okay. So this is the relaxation time, how you determine. So later we'll come back. So why this is a relaxation time defined as m times b. So you can see later when we calculate the equation. So then this is the m times b. So what will happen? So the particle mass you can determine, right? So pi over 6 times dp to power 3 give you the volume. This is rho p. This is the density of the particle, right? So this will give you the particle mass. Okay, this is the m. And then the mobility, right? So you have the definition, right? So it's the, by definition. So we show you the mobility, right? By definition, is the Cunningham correction factor divided by 3 pi times zeta that dp. dp again is the diameter of your particle, right? So if you simplify this, so then you get so this is called the relaxation time. So usually the unit will be in order of time. So let's say in second. So this is the second, right? So how much time right needs for the particle to adjust to reach a new state, right? When you apply force. So of course you can see this relaxation time will be equal to the density of the particle times the dp squared. So this is the kind of the size of the surface area of the particle, Cunningham correction, viscosity of fluid, right? But this is if you look at this equation, it's kind of makes sense, right? If you have a larger particle, right? So that means you have a more momentum or inertia, right? So it's more difficult for you to adjust, right, to your velocity, right? So therefore, you can see the relaxation time, of course, will be depends on the particle size, and then time the density, basically the mass of the particle and now for the viscosity here. So kind of the reason, right? Reasonable. But we'll go back and give you some ideas of why you come up with this tau here. But just to give you the definition. Okay. So just give you some quick ideas. Okay, so what's the relaxation time for a typical particle size? Okay, so let's say you have different particle size. This is a particle diameter. And then you can calculate, sorry, your tau, different size. So in order of seconds. So you can have different particle size, say 0.01, 0.1, 1, 10, and 100 micron, okay? And then see how fast they can adjust, right? So this is a 7 times 10 to the power minus 9. So you don't need to worry too much about the number at the front, but you cannot look at the order of magnitude, right? So you can see, if you look at the order of magnitude, so for a very small particle, right? So the relaxation time, of course, is shorter, right? Smaller particle, of course, you have a shorter relaxation time, right? So it makes sense, right? Smaller tau, right? Or shorter relaxation time. Makes sense. But you can see that actually, so even a 100 micron, right? 100 micron particle, the relaxation time is also very short, right? Quite short. It's about 10 to the power minus 2 seconds here. So basically, a particle somehow can adjust the speed, right, or adjust to a new condition, right, of a force, right, quite fast, okay, under typical conditions. So let's say we look at some motion of the particle. So let's say we simplify cases, okay? So let's say we just for a simple case. Let's say we follow a straight line acceleration. A straight line acceleration of a particle, okay? So that means we are looking at, say, initially at a particle. So they say have a zero velocity in a still air, and then you release the particle, right? And then you drop the particle due to gravity, right? And then eventually, so you reach your settling velocity or terminal velocity, right? So initially you have a zero, right? Yeah. So this just to give you some simple idea of some more simple cases, okay, to try to understand the tau, okay, the relaxation time. Okay, so we just describe this and try to understand the tau, okay, using this straight line acceleration. So basically, we are looking at the case, say, acceleration of a particle, right? So we have a particle here that is a release say at with a zero velocity. So we simplify our discussion. Say you have a zero velocity, okay, and then you in some still air, okay, and then after certain times, right? So after certain time t, right? After certain time. So if you reach the terminal velocity, right, due to the gravity. okay, due to gravity, right? So now we want to look at so how long does it take, right? So this is more related to the tau, right? So the idea is how long does it take, right, to reach this terminal velocity or settling velocity? Okay, and then how you link it to this tau here. So of course, we can just do a simple force balance, right? So basically, you have an aerosol. So I think we did this many times. We have this gravity, right? Fg, gravitational force. And then you have this drag force, right? And opposite. And then you can do the force balance, right? If you're interested, starting from F equal to ma. So that's b dt. dv dt, that means the change velocity, right, against time is the acceleration, right? So we don't worry about this. So the force will be Fg minus Ft. So then you can equal to minus mg is a gravitational force, right? Drag force will be 3 pi theta v, the velocity of the particle, size of the particle. Do the correction, right? So dp, remember dp is the diameter of the particle, v is velocity of the particle, zeta is the viscosity of fluid, Cunningham correction. So this will give you the drag force. This is the gravitational force to minus, right? To be equal to mcv here. Okay. So now, so let's say with this equation, okay. So with this equation, so let me multiply. So let's say I'm multiplying the mobility. Okay, in this case, let me say I multiply speed to all these terms, all the term here. Okay, so now you will have mv times g, right? So I times the b here minus. So maybe let me rearrange this. So I put this term here first. So mv dv dt. So I times the b here equal to mvg, right? B times here minus. Right, I just times b into each term. Okay, so now if you remember, right, by definition, right, just say by definition, m times b is called the tau, right? So this is the tau. M times b is the tau. So therefore, so you can see here, this is the tau dv dt. So this is the tau g, right? Okay. So now b, so you know the b value. B is the mobility, right? So it's the cc, right? The Cunningham correction factor divided by 3 pi theta dp, right? So I can substitute to here. I can cancel term if you pay attention. So basically, if I times the b to here, so what we'll get? So we only have the v velocity left, right? Because cc will cancel. And also your 3 pi theta dt will also cancel, right? So these 3 terms, also this term will cancel. So you only have the velocity left here. You see the point. Okay. So now I can rearrange this equation. Okay. So you can see this is the velocity v, right? So I can put here, I can put my delta t, right? The time to the other side. Okay, and I have some constant. So if I'm okay with this, then let me rearrange this equation. Okay. So what I'm trying to do now is, so you can see here, right? So I can put my dt to, so let's say maybe I can put the whole terms to here, right? So I give you this term here. And then dv dt go to the other side, tau become 1 over tau here, right? And then I take the integration, say from time 0 to time t, and then my velocity will change from initial, we don't have any velocity, right? So therefore v equal to 0. And then at time t, or at a given time, so let's say we don't VTS, so let's say VT. So at given time t, then we'll have a certain velocity at given time t, right? But now you can see I put a term here. This is the settling velocity, right? So where does this term come from? So this term come from this term, right? The tau g. So if you remember, right? So what's the tau g? Tau g is equal to mb, right? Tau means m times b, right? Times g. Okay, if you remember, let me, if I rearrange, this is mobility times the gravitational force. Mg is the gravitational force. So this will also equal to the VTS, right? If you remember the mobility times the force, if the force is the gravitational force, this is the settling velocity. So therefore, tau g will give you the settling velocity here. Okay. So then I can take the integration to this, right? So yeah, okay, right? So I think it's quite straightforward. So then I can take the integration and then do the substitution. So by doing this, so you can find the velocity change with time will be equal to VTS 1 minus over tau. So if I solve this equation and I do the substitution, so you get this. So this equation tells you so how the velocity of your particle change with time will be equal to your terminal velocity times this bracket, right? 1 minus exponential minus times t to the tau, right? Here, okay. So now you can look at some physical insights of this tau, right? So it tells you tau is called the relaxation time, right? Basically give you some idea, right? So how fast the particle can adjust to a new state. Okay, this is called the tau by definition. Okay, but what's the meaning of tau here? So you can see here, right? So if your time equal to 1 tau, so what will happen? Say 1 tau. So you can look at this equation, right? So if your time equal to tau, let me say 1 tau here. So what will happen? So that means if your time equal to tau means your relaxation time. So this will become tau, right? T will equal to tau. So this will become tau over tau means minus 1. That means this will be 1 minus, right? 1 over e. Okay. And then times your terminal velocity. This is your ultimate velocity, right? So therefore, you can see here, right? By using this equation. So your relaxation time, tau. Okay. So basically, it means the meaning is the time that a particle, right, to reach. Now you can see it's a 1 over 1 minus e, right? So equal to about 63.2% of this terminal velocity. That means your VTS or settling velocity. Do you see the point? So more meaning idea for the tau give you is the time that a particle, right, to achieve maybe around 62, sorry, 63% of your terminal velocity, right? So this is what tau means here. So that means if I try to draw a graph, okay, so let's say the y, so the x-axis here is the tau, or you can say is the time, but I express the time in terms of tau, not say from 0 to 1, 2, 3, 4, 5 seconds. Let's say this tau, say this is 1 tau, 1, 2, 3, 4, maybe 5. And then this is the velocity. So let's say I normalize this to your terminal velocity. So that means the maximum you can have is 1, right? So that would be 1 maximum. So 1 tau means you will reach about 63%, right, of your final velocity. So there about 63% or 0.63 here. So that means at 1 tau, so you will have this, right? So about here. And then you can see, of course, when time increases, and then eventually, so you will reach your terminal velocity, right? Okay, so eventually, if you give a long time, so you get 1, right? So you reach your settling velocity here. Okay. So then usually you heard about people talk about 3 tau, right? So people are interested in the 3 tau. So when the time equal to 3 tau, so that means if you look at the equation, so you can put this t become 3 tau. So that means it's 1 minus e. Okay, this is 1 minus 3, right? So that means you will reach around 95% of your terminal velocity. So when you say it's a 3 tau, okay, so this is the meaning of 3 tau. And also, I hope that at least based on this relatively simple analysis, so you have some more idea, right, about this tau means, the relaxation time. So at least you have some more idea now. So what's the meaning of 1 tau? Or now why people interested in 3 tau? Okay, so it's this one. But remember, so this equation, so you, of course, you start with a initial velocity is a v0, but you can also relax this relaxation time, this assumption. You can also do this integration, but you are not set the initial velocity is 0, right? So you can have an initial velocity, right? So if you have some initial velocity, so you can have this equation. I changed the notation a little bit, but the result is the same. So now you will have this, we call the end velocity, that means your terminal velocity in this case. And then V naught is your initial velocity. Okay, so you don't need to assume it's 0. Of course, you get this back to 0, you get the same equation here, right? So if your initial velocity is 0, does it make sense? So I think that this simple analysis give you some more additional information or refresh your memory. So what's the meaning of tau? And also now you have some more idea about, so what's the meaning of 1 tau? And people talk about 3 tau. Okay. And also you can see why you want to have this n times b, because eventually this will give you the time scales. Okay, and then this is the relaxation. Okay, because of this term, this tau, okay, so you will find that this tau will be equal to n times b. Okay, so this will give you ideas. Okay, because of the time, so let's take another 10 minutes break here, and then we'll come back at 1:45. Okay, if you have any question, so feel free to ask during the break. So let's take a 10 minutes break here. So we come back at 1:45. So what's the meaning of the end velocity? And is it the same as the VTS? Yes, in this case, this end velocity is the VTS. Okay. So if we apply to our situation, so the end velocity would be the VTS. Yes. Is it clear? Okay. So again, okay, yes, good. Okay. So this is more like the general equation. Okay, if you want to apply in different situations, like if you want to assign a initial velocity right equal to 0, then you can more likely using this equation. Okay. So now we're going to move on to talk about another parameter called the stopping distance. So we are looking at distance. Okay, a particle will travel. Okay, until it adjusts to a new condition. Okay. So we are looking at, say, a distance. So that a particle travel so until so it has adjusted to a new state or new condition. So that means the idea is that eventually stopping, right? So we can also argue, right, the end velocity, the VE, the end velocity. So we use the term end velocity will be equal to 0. In this case, right, it's more the stopping distance. Okay. So to calculate the stopping distance, right? So we can start with we can kind of replace the velocity, right? So let's say the velocity will be just a dx dt, right? X is the distance, right? You travel, right? So this will give you the velocity, right? Of course, the distance will change with time. So therefore, you can come back to this equation, right? So we just show you here. And then you can just rearrange the equation and then you do the integration, right? So basically, you can see v equal to dx dt, right? So therefore, you can have this term, right, replaced by dx dt. And then you do the integration with time, right? So what I'm doing is, so you still have this general equation, right? Vt is the velocity at given time t, right? So sorry, I have to blank here. So if this one will be also equal to dx dt, right? Dx dt. So dx dt here. So therefore, you can just take the integration, right? Say from 0 to a certain distance, right? You stop, right? And then the time over a certain time, right? So by substituting these, so you will find that your distance, so as a function of time, will be et times t minus tau So if you solve this distance, say from time 0 to t, so the distance, right, traveled by this the particle. So you come up with this. This is the distance as a function of time. This is your end velocity times t. This is the time minus tau times ve minus v naught. V naught is the initial velocity. Okay, your particle head. and then times this 1 minus e, okay, to power t over tau. Okay. So now we are interested in looking at this, what we call the stopping distance. So you can say, or we can say, so if the times is sufficient long enough, say tends to infinity, and then you will stop, right? Eventually, so your particle eventually will stop. Okay. So when the times go to infinity, means that you have a sufficient long time, and then your particle will eventually stop. Right. So when time tends to infinity, so then your end velocity will be 0, right? Because you stop. So we are looking at the stopping system, right? Here. So therefore, you can calculate, right? At that time, when your velocity given sufficient time, and then your velocity is 0, means you are looking at the stopping distance, right? So the distance you travel, right? So therefore, your stopping distance S, okay. If you look at this. So your end velocity is 0, right? So that means this term will become 0 because this is 0. So this is 0, right? So this is minus. And minus will become plus, right? This will become tau v naught. And then because this is infinity, so you can see this will become 0, this term also. So therefore, your stopping distance can be determined by tau times the v naught, your initial velocity here. So in case that you want to calculate this, so because you know the tau, right? Tau means the mb times v naught, right? So this is mb, right? mb is the tau. So you have this whole term, 3 times your v naught. So if you're doing this, so you can just calculate your stopping distance. So in case that you know the size of the particle, dt, the density of your particle, your initial velocity, right? But most important message is, of course, we know, right, the stopping distance will depend on your initial velocity, right? So if a higher initial velocity, right, you have a longer stopping distance, right? So this makes sense. Okay, then let's see the stopping distance. So just to give you some typical value. So I understand I sometimes I use a capital D, sometimes as a small d. So they talk about the particle size. Okay. And then so let's say I fix the initial velocity is 0, v0 equal to 1 meter per second of your particle. Okay, I'm looking at the stopping distance. So let's say just to give you some number. So this is 0.1 micron in diameter, 1 micron and 10 micron. And then my initial velocity, okay, so let's say it's 1 meter per second. I assume some density, and also now you know the size. This is the viscosity of your particle, of your gas. Then the stopping distance for a small particle would be so you can see that for a very small particle, the stopping distance is a micron, okay, 10 to the power minus 6, okay, or even smaller. So you can see 0.1, the stopping distance will be very small. And then for larger particle, of course, we apply the same velocity, right? So a larger momentum inertia, so you know you have a longer stopping distance, right? So you can see here, right, from the equation. So therefore, you can see it's in the centimeter here, okay? So this will give you somehow the idea about the stopping distance. Okay. So then we'll combine the information we have here about the tau and also the stopping distance, right, in some straight line acceleration. So can we also try to apply this into some curvature, okay, or curved movement. So because we know the particle is not always move in a straight line, right? So you can have travel some curve and then do some bending, right? So you have so you all have this bend, curvilinear movement, right? So you have this here, okay. So you can imagine, right? So you can have a particle here. So you introduce a particle to kind of this tube. So you have this bending. Okay, so you have a particle here. So let's say if I know the streamline for the gas, kind of the streamline here, so the gas will follow here, right? So this is the streamline. So this is to give you some idea. So then we have some particle here. Okay, so what will happen to this particle? So of course that depends on the size of the velocity of the mobility. Okay, so you can imagine, right? So some particle. So what will happen if you get a small particle, right? So what they try to do is that they more or less, right, try to follow the streamline, right? So it's something like this. But you can also, right? Sometimes you have some larger particle, they will not follow the streamline perfectly, right? So they may be something like this, right? So they may not follow the streamline perfectly. So it depends on the size of your particle, right? Are you okay with this? So you can argue, right? So this particle, so somehow they can follow the streamline perfectly. So for this one, okay, so here you follow the streamline perfectly. But you can also, in some cases, your particle does not follow the streamline. So maybe your real particle or some larger particle, they not follow the streamline here, right? Not here. So then how we can look at this phenomenon, okay, try to using like the stopping distance to determine this kind of the delta, right? So you have this delta here, the displacement here, right? The displacement here. So if you look at the story, so let's say I think the textbook gives you some detail, more detail how to derive this delta, the displacement here. This is the perfectly follow streamline, but in case you don't follow streamline, so this is delta. But here we have tried to have some qualitative discussion. So if you look at the velocity of the particle, so mainly you have two components, right? So one is called the Vx, and then you have this Vy, right? Vy here. So I have two components. So initially, so in this point, so you have two components here. So then when you have this curvature, so what will happen? So after a long time here, so in case you have particle here, so you still will have this Vx, right? So you still have this x component, right? Velocity. But what will happen to your Vy component here, your Vy? So when you travel here, so you can move like a more parallel to the tube. So your Vy will become 0, right? If assume, so somehow you bend this, and then eventually, so you just travel like a parallel to this surface, right? The tube. So that's why in this case, you still have this Vx component, right? But your Vy will become 0, right? To 0. Are you okay with this? So in case you don't have any more, your z, the yz in the y position, in the y direction, right? And you will just move horizontally, right? Here. So therefore, you can see that is in your Vy. So eventually, you will look at some of deceleration, right? So Vy will become Vy, and it will become 0, right? Initially, you have a Vy component, right? But then eventually, your Vy becomes 0. Basically, it has kind of a deceleration, right here. You have a deceleration, right, in your y direction. Okay. Does it make sense? So therefore, you can argue, right? This is a delta. It's a more like the stopping distance, right? You see the point. The delta, you're looking at the displacement compared. This is somehow perfectly follow the streamline. And then in some cases, you are not for the streamline, but you have this displacement. This delta, qualitatively, you can argue, right? So it's more like the stopping distance, right? For your y component, right? Vy here. Because initially you have a Vy certain value. But after that, after bending, right? So your Vy becomes 0. So therefore, you can see the delta is more like the stopping distance, right? So also say when Vy become tends to 0. So this is more like the delta. It's more like you can roughly estimate, right? Using more like the stopping distance we just discussed. Okay. So now, if you agree with my, it's more like a qualitative discussion. Okay. So that means that somehow your stopping distance gives you some idea about like the displacement, right? Say somehow away when you compare to say if the particle follow the streamline perfectly, right? The delta here. So this delta can also give you some idea about how to collect the particle, right? So in this case, we want to introduce a term called the Stokes number, STK, Stokes number. So basically, the Stokes number tells you the behavior of a particle. It is like the model, the curved, right? The linear motion. And also by definition, the Stokes number looking at a ratio. So they're looking at the ratio of the stopping distance. We are talking about the delta here. To some characteristic length scale. So I'm going to explain to this. Okay, this is the definition for the L. So let me write down the equation for you first. So this is the STK Stokes number. It's the stopping distance, right? Stopping distance is the tau, sorry, S. So let's say S over certain characteristic length. So we're going to talk about what's the physical insight or meaning of this ratio. So the top, if you remember the stopping distance, right? It's just the tau, right? Times the V, the initial velocity. Okay, then this is also equal to rho dp cc, initial velocity. Okay, theta here, and then you have this L. So you see this is the stopping distance, right? This term is the stopping distance. It's the density of your particle. And then you divide it by the L. L is kind of a characteristic length scale. Okay, so let's talk about this Stokes number. What's the meaning? So one thing is, of course, you see here, right, the Stokes number tells us some behavior, right, of the particle in a curvilinear motion. And more important is this Stokes number people use to look at is to call the particle collection. Okay, the Stokes number is look at the design. We call the cutoff particle size. In the impactor. So what's that mean? Okay, so let's qualitative discussion here. So if this is an impactor, okay, so you can imagine. So this is more like the space, right? The tubing, or the radius, or the size of your particle, the diameter, or the radius of your tube, right here. So what will happen? If so, let's say this L. So if say I define usually people talk about the radius. So let's say maybe just talk about the radius here, or let's say this is L. And then this is the radius of the tubing. So this is fixed, right? So this is the size of the tubing, of the radius of the tubing is fixed. Okay, this L is fixed. But this the delta can change, right? Depends on the size of your particle, right? Am I correct? So you can see here, this delta is the stopping distance. So what will happen? So you can see here, right? So let's say if I have a small particle, so you know the small particle will follow the streamline, okay? And then you have a small delta, small stopping distance. So you will not, you just follow the streamline here. But what will happen if we have a large particle? So you have a large particle, what will happen? What happened to your delta? So your stopping distance, right? For large particles, I mean your dp will increase, right? So you have a large particle, intuitively, you know, the particle will not follow the streamline. So what will happen is your larger particle, if your particle is larger, right? So you come across with this. And then some of the large particles can hit the surface, right? Of the inner surface of the tube. That means your delta would be equal to, say, L. Right? So if it's equal to 1, then you can argue, right? Somehow they can just hit the surface, right? So your delta will increase. So then you hit the surface. And then what will happen is, so they cannot follow the streamline. And also you can somehow have the impaction can happen, right? You see the point intuitively. So because of, for example, I fix this characteristic of my this length. This is like the radius of my tubing. In this case, if a small particle, right? So they just follow the streamline. The delta is very small, so you will not hit the surface. But if a larger particle, so we know that the big particle will not follow the streamline, and then you can hit to the surface, right? So what's the displacement? You can calculate using this delta, right? For larger particle, you have a larger delta, right? When your delta larger than your L, okay, then you have the impaction can happen, right? Intuitively. So therefore, by looking at this Stokes number, so this will tell you some ideas of whether your particle will follow the streamline or not. So let's say if you now have some more ideas. So what will happen if your Stokes number is much, much larger than 1? So that means your stopping distance, right? Your delta will be much larger than the length, your characteristic length, that means the radius of the tubing, right? So therefore, it's a large displacement. So therefore, when the Stokes number is large, okay, so basically means your particle does not follow the flow, right? When your Stokes number is large, that means you have a large stopping distance, right? So your particle cannot follow the flow. So basically, you can collect by impaction, right? But in the other case, that means if the Stokes number is small, so that means that you are talking about some small particle, right? So that means you can argue, right? The particle can adopt the change. quickly, right? So then you don't have any collection. So therefore, you can see that this Stokes number, right, can also give us some more idea, right, about the collection of the particle. If you want to design the collection of particle, say by impaction, right, in this case, so I can look at the Stokes number, right, because if I want to collect the particle by impaction, right, so I need to have a large Stokes number, right? So because of to do this, so you need to have so your Stokes number is large, so that means your particle can be collected by impaction, right? But if your Stokes number is small, now you know that means you will just follow the streamline, so there will be no connection. So therefore, this Stokes number, okay, can help us to design the device. So how to say collect the particle by impaction, okay, by impaction here. And as of course, you just by looking at this. So if you want to say collect the particle, right, or some particle, okay. So that means by impaction. So what you want to do is you want to have for given particle size, right? If you want to collect this particle, so you want to have a large Stokes number, right? So that you can collect the particle by impaction. So by doing this, so if you look at the equation here, right? So you know the size of the particle you want to collect, okay? And then maybe you have some idea about the density of the particle. So these are something you cannot play around, right, in your device. But if you want to collect this particle, right, the particle, you know you want to have this number big, right? So therefore, you want to have a large number here. So in practical, so how we can do this is, of course, one thing is this is the velocity of your particle, the V0 here. Okay, the velocity of the particle. That means your particle velocity here, right? So therefore, if you want to collect the particle, so one thing is that you're interested, so you can increase the velocity, right? So then if you increase your velocity, then you can collect your particle by impaction. I think it's intuitive if you think about this, right? And also, good. So I think the people also ask about, so how you define this L, right? So L, in this case, the L is the length, the characteristic length, okay? In this case, you can see, right? So the delta, if you look at how you want to define your characteristic length, the delta is the displacement, right, of your particle in this y direction, right? Okay. So if you want to compare also in this direction, right? So you are looking at some characteristic length, right, in your system, right? Also somehow in this direction, right, or related parameter. So one reasonable is to look at is the radius or the diameter of your tubing, right? In this case, because this will help you to compare with your displacement here. Does it make sense? So therefore, in the picture I show you here, the characteristic length we choose will be the radius of your tubing. That means it's reasonable, right? To look at here, right? To compare with your delta, right? Does it make sense? If you want to choose a characteristic length for the impaction. So you want to choose, in this case, the radius or the diameter of your tube. Will I answer your question? Good. So therefore, this ratio will give you the insight, right? If the delta is larger than your L, right? Then you know you have an impaction, right? If this delta is smaller than your L, then you know this no impaction can happen. So therefore, one thing is to do this for collection is to increase the velocity, okay, of the particle, of your gas, and also reduce the length, right? So you can see, right, if I replace with a tube, more narrow, right? So you can imagine, right, I can allow more impaction can happen, right? So given the same delta, right? So therefore, another thing is that you can design, you put a more narrow space here, right? So then you allow more impaction can happen, right? Because if I have a larger tube, then you have a less impaction, right? Then you have a smaller tube. Of course, you also affect the velocity. You need to play around. But most of the time, people will play around is the velocity. Okay, and then to achieve a high velocity, so we will use the pressure probe. Yes, you are right. So there's a question is that we care about the Stokes number because we want to set the device to collect specific particle size, I think, by impaction. Yes, you are right. Yes. Only purpose. So I think it is the main purpose, not the only purpose. But of course, the Stokes number is help you to design for the impaction. But more idea is to help you to understand so whether the particle will follow the flows or they don't follow the flows. But of course, correction by impaction is something, someone wants the impaction, someone they don't want the impaction, someone wants the correction, someone they don't. But I think in more general, the idea is that this Stokes number is to help us to understand the behavior of a particle, okay, in some curvilinear motion. And of course, using this number, we can have some better ideas of whether the particle will be removed, okay, from the gas stream by impaction or not. But this is may not be the main purpose for the Stokes number. But the Stokes number means to understand the behavior of the particle in some curvilinear motion. I think that would be the ideas. Does it make sense? Good. Okay, so now you will have some idea about this Stokes number. Because of the time, I think I'm going to stop here. So, but next week, so next lecture, so we're going to some more detail. So how we can collect the particle by impaction, and also how we have some more insight to talk about this we call the Stokes number here. And also, so we're going to have we're going to post the homework assignment, okay, tomorrow. I think the TAC, are you here?
Yes.
Yes. Yeah, so we are going to post the assignment one on the whiteboard tomorrow, okay? And then we'll have 2 weeks for your assignment, okay? And also, so I think the video will also be posted on the website right here.
Yes.
Okay. So we'll also post the lecture, the videos, okay, onto the website. Yeah, so is there any question from the class before we leave? Okay, then if not, then I will see you after the Chinese Lunar New Year. So Happy New Year to all, and then see you soon.